You're crushing a brutal training session. Your smartwatch shows everything looks normal. You're in the zone. But 24 hours later, you can barely walk. Your legs feel like concrete blocks. Here's what's shocking. Your heart was actually screaming warnings the entire time. Not through heart rate, but through a specific heart rhythm that nobody knew could predict muscle damage. This is the first study to crack the DOMS prediction code using standard heart rate monitors. And we're not talking about some vague correlation. We're talking about detecting the exact moment your body crosses what the researchers call the transient point of no return. For decades, coaches have been flying blind with DOMS predictions, waiting for athletes to report soreness, but by then, the damage is done, literally. Langmar and his research team suspected that there had to be a way to catch DOMS before it strikes. They knew that delayed onset muscle soreness doesn't just appear randomly. There's a specific neurological switch that happens during exercise when your body crosses from the beneficial stress to the damaging stress. The problem? That switch happens hours before pain develops. To our knowledge, no such primary damage point has been detected by heart rate variability monitoring. But here's what excited these researchers. They suspected your heart rhythm patterns could capture that invisible moment when cellular damage begins, what they call the acquired piezo2 channelopathy, triggering that cascade towards DOMS. Instead of measuring heart rate variability, HRV for short, against time like everybody else, they flipped the entire approach on its head. They mapped HRV parameters against heart rate itself, and this game-changing method revealed hidden patterns that traditional analysis completely misses. For the test, they recruited 19 elite handball players from Hungary's National Academy Under-16 squad. Then came the real test. Each athlete endured a brutal DOMS-inducing protocol on an isokinetic dynamometer. We're talking 15 max effort repetitions across 6 relentless sets of knee extensions. Half the team battled through concentric contractions, the other half through punishing eccentric contractions. But here's where it gets sophisticated. They tracked 5 key heart rhythm measurements. Sample entropy, that's the heart rhythm's complexity, plus RMSSD, SDNN, low frequency power, and high frequency power. At 8 and 24 hours post-exercise, they assessed muscle soreness using validated pain scales, then divided athletes into low DOMS and high DOMS groups based on their pain scores. The researchers were right. They discovered something nobody had seen before. They could predict severe DOMS with perfect accuracy using heart rhythm patterns around a critical 120 beats per minute turning point. Here's how they cracked the code. During intense exercise, heart rhythm complexity shifts into predictable patterns, while the 4 other heart rhythm measures all increase. The breakthrough came when they analysed who would suffer the worst DOMS. Athletes destined for severe muscle soreness showed a telltale signature. Below 120 BPM, their heart rhythm complexity was slightly lower than those who barely got sore. But above 120 BPM, it climbed much higher, a pattern that screamed impending muscle damage. This 120 BPM turning point is where your body's position sensors become overloaded and shut down to prevent damage. When comparing both DOMS groups, all measurements were highly significant. So what does this mean for your training and coaching? The researchers outline 3 game-changing applications. First, this represents the difference between what Dr. Hans Selye called eustress versus distress. Good stress that promotes adaptation versus bad stress that causes cellular damage. Your HRV patterns can now distinguish between these states in real time. Second, this research reveals why some athletes recover faster than others. The low DOMS group maintained what researchers call frequency-coupled stress buffering. Their nervous system stayed synchronized. The high DOMS group showed decoupled patterns, indicating impaired communication between the brain and the muscle. Third, the researchers showed that electromagnetic stimulation therapy can actually reverse the damage by reinvigorating piezo2 from its channelopathy. This suggests the cellular damage isn't permanent, and there are potential interventions that can restore normal function. Most importantly, this research establishes the foundation for real-time DOMS prediction, opening the door for future monitoring applications. This research comes from heart rate variability alterations during delayed onset muscle soreness inducing exercise with piezo2 interpretation by Gergely, Langmar and colleagues. Published in Sports, Volume 13, Issue 8, August 2025. You'll find the full link and citation in the show notes. Sports is an open access journal published under the Creative Commons licensing. Thanks for listening to Sport Science Decoded, where we take you from research to application in 5 minutes. If you enjoyed the show, please consider following. Sport Science Decoded is available on YouTube and all major podcast platforms, with episodes every Wednesday and Friday. If you have a sports science paper you'd like us to break down in this format, email us. Details are in the show notes. And if you're with a journal or publication interested in research, communication, or partnerships, we'd love to hear from you.